चेंज करना होगा ना.
Yeah, I will do. Okay, we are live now.
Wait. Hello. Am I audible? Right? Okay. So hello everyone. Right now, so this will be our second Novice session. Let me introduce about our team, what we do, IICPC. So IICPC stands for Inter-IIT Competitive Programming Conclave, and it was started as an initiative to spread competitive programming across the country, across all the institutions. And initiative started by me. I use my friend Aitya Misra and Gauris Valiga. So we are having one session in a week for Novice Camp. So let's introduce our sponsors as well for the camp. Dhruvil, can you change the slide? Okay. So we have AlgoZenith with us. I mean, pretty sure you all would be knowing it. Vivek Gupta is the founder, and he also took one session for us. It's a premium platform for intensive placement preparation, comprehensive programs, DSA development, competitive programming, whatever, everything. And student from like this is one of the thing like some guys also have went to Google and all interns. And we have another sponsor that is 0xPPL. Can you So 0xPPL empowers the next generation in crypto and Web3. Okay, the founder that is Prasna Sankar, he was earlier the founder of Rippling as well. I mean, if you don't know about Rippling, it's like $10 billion company right now, so it's pretty well. And even 0xPPL is quite well. So right, he was earlier rank one in India in top coder, ACM, ICPC, Google Code Jam at age 18. He had hired several ICPC world finalists, and so if you are one of them, or if you are a guy who has fired for competitive programming, you can reach to him with his mail ID, right? Like it's like prasna@0xppl.com. Okay. So let's talk a little bit about the camp. So those who are new, who have not registered yet, please do register on icpc.com. And so we will be having the camp till July end. And right now, this session will be taken by Ashish Ahuja. He's from IIT Kanpur, candidate master on Codeforces, and we'll be taking some problems as well from Codeforces concepts to make you like competitive and 2 pointers. Right. Next session will be by Saurya Pandey. We have been. I think you all might have seen the posters and all. So that will also be an important session, and that is for both advanced and novice session. Okay, advanced and novice camp. It will be included, and it's like Saurya Pandey. Please do make that moment and make sure to attend that session as well. He is from US and like he is I think a bronze medalist, so would be pretty good for all the math lovers here. So we can start the session right now, and also I mean we have to remind that the certificates will be providing only if you have 75% plus attendance. So make sure the attendance is pretty good. Like still till now I can say that's 230 something. So let's see. Fine. Ashish, can you start? Hello, Ashish.
Yeah, sorry. Let's just start. Uh, so hopefully the screen is visible, and yeah, let's start. So today's session is on two pointers, right? And let's just start with a brief introduction to what two pointers is. So, like in any given problem, we are given some data, right? Like it could be an array, it could be two arrays, it could be a graph, and we got to use that data to do something, right? Like that is what the problem is. But the idea behind any problem which uses two pointers is that we essentially use two pointers to process the data. Like for example, if it's an array, we will use two pointers to iterate through the data, and like in the case of an array, each pointer will only move in one direction. So that makes sure that the algorithm is like linear time. And we'll come back to like what exactly it is. Let's just see a quick animation of like a problem which we will solve to give you a brief idea of what it is. So yeah, this is a problem which we will solve soon, right? And like you can see, there are two pointers, L and R, and like basically we will come back to exactly what is happening here, but that's just a brief idea. Like you have an array, you have two pointers which iterate through the array. Like they start initially and then they iterate while we are checking or doing something, right? So yeah, let's continue and let's start with a basic problem. So the basic problem is one which is called subarray sum. So the problem is basically that we are given an array of n integers and a target sum s, and we need to find any subarray whose sum is s or report that there is no such subarray, right? So it's a fairly standard problem, nothing too hard, and there is more than one way to solve this. But we will solve it in linear time using two pointers. Okay, so let's just look at an example. So let's say n was equal to 8 and the sum is also like the target sum is 8, and like let's say this is the example array. So down here you can see a possible answer which is highlighted in gray, right? So 2, 5, 1, it sums up to 8. So we need to identify if there is such a subarray in the given array or say that there isn't any. So let's see how we will do this using two pointers. So essentially, as the name suggests, two pointers means you have two pointers, and each pointer essentially points to a given element. It's basically an index, right? So let's say we have two pointers, left and right, so which are depicted by these arrows, right? So what we do is we maintain both pointers we to the initial element of the array, right? And we want the sum to be exactly s. Like we want to check if there is a subarray with exactly s. So initially both the pointers will be pointing to the first element, and we keep moving the right pointer. Like one of the two pointers we call the right pointer, the other we call left pointer, because the right pointer is always to the right of the left pointer, right? We keep moving the right pointer to the right till we reach a point where the subarray between the left and the right pointer exceeds s. So like let's say both the pointers point towards 1, so the sum is 1, right? 1 is less than 8, and like if you forgot, like the target sum was 8, right? So now we move the right pointer to the right by 1. So it's 1 and 3. 3 plus 1 is 4, which is again less than 8. We move to the right again by 1. 3 plus 2 is 5. 5 plus 1 is 6. 6 is again less than 8. Right? But then the moment we move this right pointer one more step to the right, the sum goes greater than 8. So we stop here. Right? Now we check, is this subarray having a sum of the target sum, which is 8? The answer is no. So we proceed. Like in the next step, now what we will do is we will move this left pointer to the right by one step. So yeah, let's just see. Uh, so yeah, like this is essentially the same thing what I just described. Uh, yeah. So let's just look at an this thing. So we stopped at this step, right? So now in the next iteration we move the left pointer to the right by 1. Now we have this subarray under consideration. Now we again keep moving the right pointer to the right. So 3 plus 2 is 5. Again, if we move to the right, we run into an issue because then 10 is greater than 8, right? So again, we move on to the next iteration where we move the left pointer to the right by 1. So both the pointers are pointing at 2. 2 is less than 8, right? So we move the right pointer to the right by 1. So the array under consideration is 2 and 5. Then again we move to the right by 1. So the array under consideration is 2, 5, 1, right? And at this point we have arrived at a subarray which has a sum equal to 8, and basically our algorithm is done, right? This is what we wanted, and if we basically reach the end, like both the pointers reach the end of the subarray without us having found a subarray of equal, which has sum equal to the target sum, then we basically report that there is no such subarray which has the target sum. So what is the time complexity? Like anyone wants to have a shot? No one. Okay, yeah, it's linear time. Like it's O of n, right? Yeah, I'll just be going slow in the beginning. Like we'll hit harder problems towards the end. Like if you are already comfortable with this part, you can just come back after like 20 minutes. Uh, yeah, that's O of n. That's linear time, right? Okay. So let's just briefly say, like, talk about why is two pointers a useful technique, right? So, usually speaking, like this is all very generic. It is not always true, but like generally speaking, when you can use two pointers, like there are always other solutions to the problem as well, and usually speaking, they often use like a map or a set. So they're just slightly slower because like the time complexity has like a log n factor, so two pointer solutions are slightly faster, and in certain cases they actually help reduce the space complexity as well. So we will see an algorithm towards the end of the lecture which helps us find cycles, and that actually helps decrease the space complexity from O of n to O of 1, so which is like a very big thing. And generally speaking, two pointers is like something with which you can easily estimate the time complexity as well, and it's easy to implement. It won't cause you many issues, like if you're using that to solve a problem. So, which is why it's like a nice technique. And yeah, someone has asked a question: does subarray means it has to be continuous? We can take individual elements. Okay, yeah, I'll just define what a subarray is. So subarray is basically a contiguous subsegment. So like you could start at 1 and you can end at 5, and you could start at 2 and you can end at 5, but you cannot do 2 5 and then skip 1 and 1 and go to 2. So it's basically a contiguous subsegment. It You cannot skip an element in between. And someone has asked, oh, we are covering linked list here as well. uh Not exactly. Yes, that can be used to solve linked lists, but uh, what do you say? It can be used for linked lists, but it's like a general two pointers approach. It can also be used for functional graphs, which is like similar to like a singly linked list. So yeah, I'm just going to showcase it to show how two pointers is like a nice technique which can be used even for graph problems. Oh yeah, let's just continue. Uh, 1 second. Yeah. Okay. So yeah. So let's just talk about what is two pointers. Like we saw an example, but just to like give like a brief description of it. So it is. I think it's like sort of like a subset of greedy, and it's very similar to sliding windows uh, problems. And generally speaking, like you use it to iterate the data till you hit some sort of endpoint, like sort of like in recursion where you have a base case, end of data collision or something like that. And you do have variations of it and generalizations of it as well, which we will see soon. I guess the time complexity of the method which you are saying will be O n square. Like two pointers means a loop of I inside another loop. Uh, so time complexity of the method you are saying will be O of n square. No, it will be O of n. And okay, so I don't have the code for this problem ready right now. So let's just you'll see why it is O of n like soon. Like I will show it in another problem as well. And like hair tortoise, yeah, we'll cover that towards the end. Like same thing. That is like technically two pointers, like fast slow. We'll see that towards the end. Uh, so yeah, and let's just briefly mention what we'll be covering from here on out. So we'll cover a few basic problems, and we'll cover a few problems which have like a generalized pattern. Like they are like problems of the same kind. You can come up with a general way to solve those problems, and if you ever see a problem, you can just pretty much blindly apply that. And then we'll see a hair tortoise, like someone mentioned in the chat, which is I mean, not the conventional two pointers approach, but it is a nice thing. So I thought I'd like just showcase it towards the end. Okay, yeah. So let's just solve. Like as I said, we just solve a few basic problems to give you a flavor of two pointers. And like some people had a doubt, why is it O of and why is it not O of n square? All that will be cleared up. Uh, so yeah, if I think people can read this problem and like, uh, yeah, you can open it up on your screen as well if you wish. Like, Yeah, I'll just give you 2 minutes to read the problem and think about it. Oh yeah, anyone has any idea how to do this problem? Sum of two values. It's again fairly standard. Anyone who has done 2 pointers before should be able to do it fairly easily. Yeah, exactly. If we sort the array, then we can do. Uh, if we sort the array, then we can do 2 pointers, one from beginning and one from end. Yeah, exactly. That is exactly the way we solve it. So yeah, let's just. So everyone is clear with the problem, right? I'll just uh, read the problem again. What is sort the array and increment left pointer if sum less than x and decrement right pointer if sum is uh, more than x. Yeah, sort of. Sort the array. Yeah, that's right as well. Yeah, standard 2 pointers. Yeah. Yeah. So yeah, exactly. Anyone who's done 2 pointers before should be able to do this. So yeah, let's just read the problem. You are given an array of n integers, and your task is to find two values whose sum is x, right? And your constraints are n is up to 2 times 10 to the 5, x and ai is up to 10 to the power 9. So yeah, it's basically we need an O of n log n type solution. Uh, so yeah, let's just look at this. So one obvious method is to use a set. I was like, okay, everyone was thinking in terms of 2 pointers, so that's fine. But yeah, you just, I guess it's obvious to everyone how we can use a set for this. That's O of n log n. The method using 2 pointers, as some people said, is we sort. We keep a left pointer at the first element, right pointer at the last element. We keep moving the right pointer to the left, and the sum of the values is at most x, and we stop when, like, if we come at two values whose sum is x, which is what we wanted, or like the 2 pointers collide, so that means like we are done. We have processed the full array. So yeah, yeah, the TC is O of n log n. It's not linear time, but like we're just like showcasing another problem which can be solved using 2 pointers. So yeah, for those who are not familiar with this, I'll just go through it in detail. So this is the array in sorted order, uh, right? So we have 110, and basically we keep moving. Yeah, okay. So we keep moving the element, the right pointer to the left till the sum is less. One second. What was the problem? And it asks you to find whose sum is x, right? Yeah. So x is given, right? So as we basically said, you keep moving the right pointer till the sum is at most x. Because the moment you cross x, then you cannot really do much. Then you basically in the next iteration you move the left pointer to the right, and you basically keep doing this till you hit a collision. So yeah, it's like the same thing is just over here. It should be fairly straightforward. You move the right pointer to the left, and then in the next iteration you move the left pointer to the right, and so on. I think similar to the first problem. So yeah, as some people said, it's O of n log n. Uh, Someone has asked how can you solve it using set. Oh yeah, I think someone else answered. So yeah, I think that is a fairly standard problem. I don't think anyone should be having any issues with this, right? Uh, yeah, yeah. I don't think anyone is having issues. Okay. So yeah, let's solve this problem. Uh, it's again nothing too fancy, but yeah, I'll just give you guys 3 minutes, like 2 3 minutes. Read it and think about it, and like uh, please post the solution if you can. when to decrease right and when to increment left. So you basically decrement the right pointer as long as the sum is less than x. Less than x. If you hit x, then you're done. If it's less than x, you keep decrementing the right pointer, and then in the next iteration, like once you hit the end of the, you start once you hit the end in the next iteration, you start increasing the, what do you say, the left pointer. Can you please explain the code? I don't have the code. Like I'll show code for some of the problems which are upcoming. Uh, okay, like towards the end, like I'll do the code if we have too much time. Uh, I'll yeah, okay. So what I'll do is for this problem, I will show the code and I will explain why this problem it is often, and it should be fairly clear. Uh, what do you say? Why it is often with this problem? Yeah, it is to some. Yeah, it's a fairly standard problem. Yeah, the time complexity is O of n log n. Like we're not improving the time complexity. It is just like a showcase for two pointers. In last one, during sorting, won't the time complexity be O of n square? No, sorting is O of n log n. You have different algorithms for sorting. Generally, if you just use the inbuilt sort, there'll be n log n. Yeah, anyone has any solutions for this problem? Books. I'll read the problem. Uh, so essentially, Valera has gone to the library. He has some amount of time uh, to read some books, and uh, basically, the library, he has taken n books, and each book takes AI minutes to read the book. Like the ith book takes AI minutes for him to read. And what he can basically do is he can start at any random I and read a continuous segment of books till he either runs out of time or he has finished reading, like he's reached the nth book. So now you need to basically print the maximum number of books that he can read. What are the solutions? Can we see the input and test cases? Oh, yeah, I'll just show. Or you can just open the problem up on your computer as well, I guess. Prefix sum and two pointers. Prefix sum with two pointers. I had a different solution, something like sliding window, yes. This is somewhere, I think, yeah, it is similar to Subarray sum question. Like this, I think there's one more problem after this, which are like, yeah, it is basically a sliding window. Like sliding window and two pointers are, more or less the same thing, sort of. Yeah, it is similar to Subarray sum, but it is slightly different because here we are basically asking for the maximum length of the segment, which has sum less than equal to x. In the Subarray sum, we were looking for any segment which had sum exactly equal to s. So there's a slightly different problem. Uh, so yeah, we need to find the maximum length. Yeah, whose sum is equal to, not equal to t, less than equal to t. So yeah, I think that's enough time. Let's just what do you say? Look at the solution. So this is the animation which I had shown initially, right? So what you basically do is you start both the left pointer and the right pointer at the initial element, right? That is fine. And in this example, this is the given array 3 1 2 1, and we want to find the longest sub array which has sum less than equal to 4, and basically the longest sub array which has sum less than equal to 4. That is a way of phrasing the problem. So what we do is left and right pointer both point towards the initial element, right? We move the right pointer to the right by 1. The current sum is 3 plus 1, 4, right? So the current sum is 3 plus 1, 4. Is that less than equal to 4? Yes, it is. So one possible answer, my camera is not visible. Uh, I think it should be visible. Can someone else tell? 1 second. I guess it's visible, yeah. Uh, yeah, okay. So essentially, 2 pointers we have left and right. We move the right point. Now we have the current subarray is 3 and 1. It has a sum equal to 4, which is less than equal to max sum 4. So one possible subarray is 3 and 1, which has length 2, right? That is fine. Now the moment we move the right pointer further to the right by 1, 1 second. Yeah, moment we move the right pointer to the right further by 1, uh, what do you say, then it becomes 3 plus 2 5, 5 plus 1 6. So that goes above the max possible sum, that we is not possible. So what we do is we move the left pointer to the right by 1, right? So now the current sub array under consideration is just 1. The sum of 1 is less than equal to 4. That is obviously possible, but we already had a sub array which was 3 and 1, which had its sum less than equal to 4, which had length 2. So we have not improved our answer. Next, we move the right pointer to the right by 1. The sum was 3, which is less than equal to 4. Then we move to the right again by 1, because we keep moving to the right till we arrive at a point where the sum of the current subarray is greater than the max allowed sum. So it becomes 2 plus 1, 3 plus 1, 4. And this is possible, which has length equal to 3. So we update our answer to 3. Then we move the left pointer to the right, we move the left pointer to the right, we do not improve anything, and yeah, we are done. So that is the basic, uh, what do you say, way we solve this problem. And we look at the code, right? Yeah, so this is the code. Uh, so we are basically just reading in all the books in a vector of ends, okay? And we have a left pointer 0, right pointer 0, it's all 0 indexed. And answer is the current answer, like, and current is the sum of the subarray under consideration. So left equal to 0, right equal to 0. We want to ensure that both the pointers are, what do you say, both the pointers are less than the end, obviously, otherwise that won't work. We keep moving the right pointer to the right till the current sum exceeds the max allowed sum, which is, if I'm not, yeah, that is t. If someone has forgotten the input format, n and t, right? T is the max time which Valera has. And then basically once we exceed it, we just backtrack once. And then if it is possible, like left to right is a subarray which has sum less than equal to t. So that is a possible answer. And answer is basically, we just take the maximum of all of those possible, and then we print the final answer. I think that should be clear. And now someone was asking, why is this O of n? Why is it not O of n square, right? So you are right. There are two loops, but two loops doesn't mean that set IO. It is just a function they have used to set like the input output stream. That is like irrelevant. Like the main part is here, right? So what basically someone asked, why is this O of n? Why is it not O of n square? So you will notice that this inner loop runs at most O of n times, right? Because the inner loop is pretty much independent of the outer loop, and similarly the outer loop will also run at most O of n times, right? So I think that is fairly straightforward. I think that clears up why it is O of n, not O of n square. I don't. I think whoever had a doubt, it should be cleared up now. And someone asked why. Okay, I think that got deleted or something. Yeah. Okay. And So yeah, that is the reason why it is O of n, not understood n square. Okay, let's look at the visualization. What do you say? Okay, let's is the speed. Yeah, just reduce the speed. Okay, so I think everyone agrees that this inner loop will run exactly n times, right? Because right is zero, and so basically it gets incremented once inside the loop. Yes, it does get decremented once in a while, but that's like an edge. It only gets incremented at the edge. So this inner loop will run n times. The outer loop will this outer loop will also run n times because left gets incremented each and every time. Correct? Yeah. So basically, these lines, line number 37 to 42, these are getting run n times, roughly like O of n with some constant factor. And these two lines, 45 and 46, they are also getting run O of n times. So it is basically O of n times some constant factor, 2 or 3 or something, which is basically O of n. So I think, yeah, that should be clear now. And you can see the same thing here. Right is going from left to right exactly once. It is not wiggling around or like moving backwards. And similarly with left. Isn't prefix sum faster? I don't know. This is O of n. Like, I don't think you can go faster than O of n. Right. Anyway, yeah. Let's move on to. Uh, so far, these were all fairly standard and basic problems. And like we will do one more basic problem which uses two arrays. So far both the all the problems we did had like the data was on a single array, the two pointers were in the single array. Now we just look at the last basic problem for today, which is basically we are merging two arrays. So given two arrays where and like we want which are in ascending order and we want to merge them into a single array also in ascending order. So the obvious solution would be to just extend one array with the other and sort it, that is O of n log n. We will see how to do it in linear time. uh, yeah, and this is just a visualization. You have two arrays which are both increasing, you want to merge them into another increasing array, right? And over here, this is I'm just showing this why. The reason is because so far both the pointers were pointing to the same data. Here one pointer will point to one array, the other pointer will point to the other array. Yeah, similar to merge sort of, yes. So the idea using two pointers is we have two pointers, one points to the one array and the other points to the other array. Let's say x and y. So x points to the first element. We set both x and y to the first element of both the arrays. At each step, we push the smaller of the elements which are pointed to by the pointers to the final answer, and then we increment that pointer. So, like for an example over here, like we've already put 1 and 2. The 2 pointers point to 3 and 6. So 3 is smaller, we push 3. We increment I points to 5, we push 5. Okay, we increment I again. I points to 8, J points to 6. 6 is smaller, we push 6. Then we increment J points to 7. And I points to 8. 7 is smaller, we push 7, and like so on and so forth. And yeah, once an pointer has finished its array, we just push all the remaining values in the other array. Yeah. Yeah, it is easy. I'm just covering the basics for people who have not covered the basics. Yeah. So I think let's start with another problem, which is called segment with good sum. The longest subarray such that its sum does not exceed s. Right? I think we just did this, isn't it? Yeah, we just saw this problem, right? If someone recognizes it, it's the same thing as books. right? So the reason we're basically taking it up again is basically this generalizes to a general-ish pattern, and so basically this is the same problem, and I'll just skip over the basic solution. It's the same thing which we covered again. We look at the code. I think some people have the same issue with the time complexity. So it's the same x equal to 0, l equal to 0. We have two nested loops, but this inner loop runs at most n times, the outer loop runs at most n times. So the time complexity is off, and that should be fine, I think, right? So now let's look at uh, different variations of this problem. So this problem is books, but like instead of finding a subarray which has sum less than equal to s, we could be wanting to find a subarray which has sum greater than equal to s. Another variation could be that we want to count the number of uh, along with just not along with finding the longest valid subarray, we want to count the number of longest valid subarrays, right? Screen freeze. I think it's fine. Okay, so yeah, these are two different variations. Uh, yeah, I think it must be on my side. Uh, Wait. Visible now? Can you hear me at least? If you can hear me, I'll just switch off the camera and like continue the session. I don't know what the issue is. Okay, I'll continue the thing. Yeah, okay. I don't know what the issue is. Sorry for that. Okay. Okay. Continuing. Uh, so yeah, I think I don't know if the last part was heard. Uh, so it's the same problem, right? Now we can have different variations of the same problem. So like instead of the sum being less than equal to s, we could have a problem where the sum of the sub segment has to be greater than equal to s, and we could also have a slight variation to this both the problems where we want to count the number of these longest valid subarrays, right? Uh, and yeah, so let's just look at why these kind of problems form a general pattern which everyone can use to solve problems, a new problem when you see them in the contest. So the standard problem, what it looks like is we want to find the longest or shortest segment or count the number of segments which satisfy some certain property. Like the property is like what do you say? Like in the problem which we just saw, the properties were like the sum of the subarray has to be exactly s. The sum of the subarrays have to be has to be less than equal to s, greater than equal to s, or you want to count the number of segments. So let's just see in what sort of problems can we use two pointers. So firstly, one of these two conditions must hold. So if a segment from left to right is good, either any segment nested in it is also has to be good, or if a segment L to R is good, any segment containing it also has to be good. So one of these two conditions has to be true, right? So if you're thinking why does it have to be true, so it feels fairly intuitive why it has to be true, but if you think of it, you cannot really keep extending the right pointer and incrementing the left pointer unless and until you are sure that, like, okay, think of it this way. In the good books problem, right, or the sorry the books problem, or which is the same thing as this. So what we are doing over here is that we keep extending the subarray till we hit the longest subarray which satisfies the property, which is less than equal to us. Now if the nested property wasn't true, so let's say there is some subarray, let's say from 1 to k, which is the best possible subarray, but from 1 to k minus 1 does not satisfy the property. So you will not, you will basically stop the right pointer at k minus 2 itself, or k minus 1, like matters on, yeah, you'll stop it at k minus 2. That matters on the implementation, like whether you stop it just at the edge of the subarray or like one element after the subarray. But the point is, you will never hit 1 to k if 1 to k minus 1 does not satisfy the property. And similarly, if you are trying to like shrink the arrays, right, if you are doing the variation that we want a subarray to have sum greater than equal to s, if you're trying to shrink the subarrays, then you want every you want the second part to be true, that if any segment is good, then any if some segment is good, any segment containing it also has to be good. So that is the reason why at least one of these two has to hold. Obviously, both of them won't hold together. Otherwise, every possible segment will be good, right? So that one of these two will hold. And the second condition is that we must be able to recheck whether the current segment is good or bad when we move the left pointer or the right pointer by one. So, like in I again, this is fairly obvious, but we're just formalizing it a bit. So over here, like when you increment or decrement the left pointer or the right pointer, you just check the sum. You can change the sum easily and just compare it to the target sum. Yeah, that is all there is in the general pattern. So let's try to code up this general pattern a bit, and this is the general pattern which is fairly useful. So we start both the left pointers and the right pointers at 0. We keep moving the right pointer to the right till what do you say, till you reach a point where the right point till the point where the left to the right pointer does not satisfy the good property. So then once you reach that point, you start moving the left pointer to the right all the way till you reach the point where finally again you are considering a subarray which has which satisfies the given good property. So, for example, in the books problem, right, you keep moving the right pointer to the right till you hit a point where the sum is greater than s. Then you start moving the left pointer to the right till you arrive at a subarray which has sum less than equal to s, and then you repeat. And then obviously there will be a statement here to update the final answer. What matters is what the problem statement is. So like in the books problem, you want to find the largest, the length of the largest segment. So you will do something like answer equal to max r minus l plus 1 over here. I think that should be fairly fine. And let's look at a problem which generalizes, which uses this generalized uh, method. And obviously, this generalized method has a time complexity of O of n, it's linear time. Because we are assuming that good is linear time and add is linear time, remove is linear time. If they're not linear, sorry, not linear, constant. So if add, good, and remove are not constant, then it just becomes O of n times the time complexity of whatever add, good, remove is. But generally speaking, you will see in any two pointers problem, add, good, remove will always be constant time. So let's look at a problem segment with a small set. So the problem is given an array A, given an array A, we need to find a segment L to R of maximum length, which has at most k distinct elements. So can anyone try this problem? How would you do this? and I think there's a lag between the like me speaking and the live stream. I think. If we encounter a duplicate, we move one pointer to it. Okay. Anyone else has any idea how do you solve this? I don't think that's right. Like if we encounter a duplicate, we move one pointer to it. I don't think that is right. Store all the elements in an array and check if it's appearing in the window. I didn't understand what you're trying to say. Like, could you elaborate? Attendance is done. I have no idea. Yes, we can store all the elements within the window in a set. If the set size increases k, or it is distinct elements. Set cannot maintain distinct elements. How will you do it using a set? I don't think that makes sense. Yeah, keep increasing R, then for each R we just keep increasing L until there are at most k distinct elements. Yeah. Using hash map, but it'll be taking more space and time. Yeah, exactly. You can basically, I think everyone has understood. Okay, not everyone. I think some people have got it. Some people are like one pointer at first distinct and one pointer at last distinct. I don't think that will work. Uh, can there be repeated elements? Yeah, obviously there can be repeated elements. Otherwise, distinct elements wouldn't make sense. So you have an array with which could possibly have repeated elements, and you're given an integer k. So you want to find longest segment which has maximum length, the segment of maximum length which has at most k distinct elements. Size of set exceeds k, then left plus plus. No, I don't think you can do this using a set. But anyway, yeah, let's just continue with the problem. So yeah, we want to show this using the generalized form. So let's just look at the, let's just refresh what the conditions were. If the segment L2R is good, any segment nested in it is also good. Is this true? Uh, if the segment L2R has at most k distinct elements, then obviously any sub-segment, like any sub-array which is nested in L2R will also have at most k distinct elements. That is fairly obvious. Why do we need a map when we do it with a set? How will you do it using a set? I don't think you can. Like if you think you can do it using a set, like please explain why. And yeah, uh, so let's just, it does satisfy the first condition. Uh, let's look at the second condition. We must be able to recheck whether the current segment is good or bad while expanding or compressing the segment by one element. Uh, so yeah, basically we need to be able to maintain a structure which maintains how many distinct elements are there in the current segment from L to R. And now there are different ways to do this. Map is the most obvious way. That is what I would do. Uh, you could do it using a set and a multi-set together, but it is messy. Like because I think you would have to have like one set and one multi-set. I don't think you can do it. I don't know if there's a function in a multi-set to count the number of unique elements in it, like in log n time or something. If there is, then you can do it with a single multi-set. I don't think you can do it with a set alone. Uh, with a map, I think it's should be obvious to everyone how you can do it using a map. Like the key is the element and the value is the frequency of the element. And if the values are small enough, you can just use an array, right? Like if the values are less than equal to n, say it's from 1 to n, you can just, or 0 to n, you can just use uh, an array. But using a map, won't it consume memory for every iteration if you create a new map? No, you won't be creating a new map. You'll be using the same map. And yeah, let's just look. So it does satisfy the two conditions, right? And let's look at the general form. So this is a general form. We know that the problem satisfies these two conditions, so it must be solvable using this general form. What we need to do is implement three different functions: add, good, and remove. Okay, and so what is add? Add adds an element to the right of the current segment, right? So, and yeah, for this problem, I'm just going to assume that the elements are less than equal to n, so that I can just use an array. Uh, you can use a map as well. If people are having like too many doubts, I'll just at the end of the session I'll just code up the map. Uh, but yeah, otherwise I think it should be fairly straightforward to use a map. Like put in a map and once count and of an element becomes two, then remove the element. Uh, Not exactly. Yeah, sort of. Yes. Yeah, exactly. You can use a map, but I don't know why you don't need to create a new map for every iteration. But yeah, let's just see the solution using an array, because that's just easier to like show in pseudocode. Uh, so yeah, we need to implement three functions: add, good, and remove. So let's just define two things. Count x is the array with which we will count uh, the number of uh, the basically we are maintaining the frequency of the elements in the current subsegment. You can do that easily using a map. I think like you can just replace count with a map and that will work. Okay, and now the next element which you need to maintain is a variable called num. So num basically is just maintaining how many distinct numbers exist on the current subsegment which you are considering, which is from L to R. Okay. Next, we need to implement a function called good, right? So what is good? Like good tells us whether the current subsegment which we are considering is satisfies the given property. Yeah. So when does it satisfy the given property? If the number of distinct elements in it is less than equal to k, so that is it's just this one liner. That is straightforward. What does add do? Add adds an element to the right of the current subsegment. For that, we increment the frequency counter by one. If the frequency counter hits one, so that means this element was not there in the subsegment before. We just extended the right pointer to the right by one. That means we have a new distinct element. So now, if there is a new distinct element, we need to increase the num, which is just the counter of how many distinct elements we have in the current subsegment. And yeah, that is it. And now we just have to implement remove. So what does remove do? Remove removes the element x from the array, right? What is x? X is basically the argument. So you are passing in the argument. Over here, you can see in this general form, you are removing the leftmost, the value pointed to by the leftmost element. It matters of the implementation. Sometimes you might want to remove the rightmost element as well, like when you backtrack like one element, like we had seen somewhere here. Wait. Oh, that was the here, right? So yeah, sometimes you might want to like remove one element from the right as well. Again, these are all like implementation details, like one-off errors, like and stuff like that. Nothing fancy. Uh, but yeah, remove just decrements the frequency by one. If the frequency was uh, one before, right? If it was one before and it became zero now, so that means it was a distinct element before. Now there is no longer a distinct element, so you subtract the number of one from the number of distinct elements in the segment, and yeah, that is it, right? So we have seen the generalized form of the two pointers thing, like, and we have shown some problems which you can solve using two pointers. Two pointers is not really a hard thing. Like you cannot have like very hard problems using two pointers. Generally speaking, if you have a hard problem using two pointers, the hard part about it will not be the two pointers part, right? So Now we will see a final part of today's session, right? Which is an algorithm to find a cycle in something which is called a functional graph. Or, as someone pointed out, it's also used to find cycles in Sigley linked lists, which is basically what a functional graph is. Sort of, not exactly, but yeah, we'll just cover that right now. And the reason we are covering this is it's not directly like the conventional two pointers thing which you will see in your day to day basis, but there is. Wait, someone has put a message. अरे मैंने बस but I wanted to ask Ashish, why can't we wait, what is the logic? Vector int v, one second, I'll just go back to, wait, this was the problem, right? Yeah, vector int set int answer equal to 0. You need to maintain the distinct elements, right? So let's say you have a set. Okay, now how will you do it using a set? Like, you have not written your logic, like you just throw the definition vector int v, that's just set int s int answer equal to 0. Okay, fine. Okay, you put your logic. While l less than array size, s dot insert array r, s dot insert. One second, I'll just look at this at the end of the session, like so that like people can leave if that part is clear to them. I'll just look at doubts at the end of the session, and I'll just finish the last part because only one thing is left. Uh, because it's a bit long, right? Okay, so now we come to the last part. As I said, this is not a conventional two pointers thing, but you don't really get like very hard two pointer stuff, right? So whatever I've shown here so far, yes, you might find something which is slightly harder, but mostly the hard part of a hard two pointers problem is not the two pointers part, as I'm showing in. I'm going to show in this problem. So again, this is technically two pointers, but the hard part of it is not two pointers. In fact, like one of the proofs like of why this works is fairly hard, like it's fairly mathematical. It's one of the problems in a book by Donald North. I don't know how many of you have heard of the book, but it's a pretty legendary book. Like there was one time where it had, I think, Fermat's last theorem as one of the exercises, like an unsolved problem at that point. And yeah, now it is like, okay, I won't like deviate, but it's a pretty nice book, pretty legendary author. So yeah, coming to the algorithm. So first, let's just like look at a small visualization. Which book? Donald Knuth. I mean, I won't recommend it for DSA or something. It's like a very hard book. Wait, I'll just type down the name. Donald Knuth, yeah. Wait, I think it was Donald. I don't want to like disgrace his name by taking the first wrong name. Like I think his surname is Knuth. I think his first name was Donald. But yeah. Okay, so yeah, let's just look at a small visualization of what we will cover, just to give you a flavor of uh, what we are doing. So wait, I'm looking for like okay, yeah, I'm gonna cover uh, yeah, KMP Nuth Morris Pratt. Yeah, that is Nuth. Yeah, he's a nice legendary guy. Yeah, I'll cover what is a functional graph. I'm just giving you an example of like, I'm just giving you like a preview of what is this is. So, like you can see, you have two pointers here. One is the green, one is the orange one. So they're both moving at like different paces, and this is a graph. They're like going through the graph, and eventually, whatever happens, something happens. We will cover that now. But yeah, I just wanted to show that it's a pretty cool thing. It's a pretty cool application of something like two pointers. But yeah, again, the hard part is not two pointers. Okay. So yeah, what is a functional graph? So it is also something which is called a successor graph, which is basically a directed graph where every vertex has exactly one outgoing edge. So you can also think of it like a single linked list, which may have cycles, or like any function which maps a finite set to itself. Uh, so obviously, a singly linked list is a functional graph, but a functional graph is not a singly linked list. Uh, but yeah, okay. I mean, even if you don't understand it, it's irrelevant. Like we'll just look at some examples now to make clear what we're doing. We're going to look at a very simple subset. And yeah, okay. So this is an example of a functional graph. So you have some values x. It's basically like a function. 1 points to 3, 2 goes to 5, 3 goes to 7, 4 goes to 6, and so on. And it's basically a directed graph. And you can have multiple components. This is not what the algorithm is applicable on, but this is what a functional graph is. And it's also sort of like a singly linked list. There is a difference, like you can see over here, a singly linked list will have a head, and over here there is nothing uh, which is a head as such. But yeah, it is a singly linked list is a functional graph, and you have this thing as an example. Every node has one outgoing edge. You can have cycles. And another example of functional graph, I just copy pasted this from the visualization website we just saw. And one thing I'll just is there always a cycle in a functional graph? No, no, there doesn't have to be a cycle. Like, okay, I mean, technically, if it matters on like the definition, like if it maps a finite set to itself, uh, then yes, there is. But a single linked list does not have to have a cycle. See, I mean, this is just I just want to showcase a cool algorithm without getting too much into details. Like it's fine if you don't understand what a functional graph exactly is, because the algorithm is applicable to a very specific type, which we'll just see. Like, let me just move on quickly, like instead of confusing everyone. Okay, so yeah, let's. This slide should clear everything up. So we will basically have a graph something like this, which may or may not have a cycle at the end. So it will contain a path which starts with the head. It could obviously each edge has only one outgoing edge, so it might have a cycle in the end. It obviously won't branch out, but it is either something like this or it might not have a cycle. So the target of this algorithm is to check whether such a cycle exists, or and if a cycle exists, it should tell us what the first node in the cycle is. So in this case, it is 4, because we come 1 to 2, 2 to 3, 3 to 4, and 4 is the first node, and the length of the cycle, which is 3. Okay, so that is the target of the algorithm in such a specific. It doesn't matter what you want to think. You can singly linked list is probably the best way of thinking about it. So yeah, it's fine if you don't understand what a functional graph is. This is the only specific type of graph that this algorithm works on. Okay, so can someone give suggest a solution for this kind of a problem? Like, I'm not asking you to describe Freud's algorithm. Obviously that is complicated. But if someone can suggest a solution to this problem. Like it's a okay. I think not everyone knows. Okay, yeah, 2 pointers, one slow pointer, one fast. Obviously, I think you know what tortoise is, the Floyd's algorithm is. But what is the obvious solution? Like, yeah, exactly. We can keep track of visited nodes. Yeah, I mean, okay, set slow to first node. I think people already know what the algorithm is. But yeah, just traverse the whole graph is the obvious solution. Like if you see this problem and you did not know we were covering Floyd's algorithm today, you would think, okay, you would never think of one slow pointer, one fast pointer. Uh, but yeah, the obvious solution is just traverse the graph. You start from 1, you go to 2, and you maintain a visited array, right? So yeah, I've just described it in text here. I'll just like you maintain a visited array like you do in DFS. You start from 1, you go to 2, you go to 3, you go to 4, you go to 5, you go to 6, and then you see that 4 is already visited. So you know that 4 must be the first node, and there is a cycle. If you reach the end, then you're done. Like there is no cycle. That's the obvious solution. Can someone tell me the time complexity and the space complexity of this solution? Attendance form accept nahi kara raha. Uh, I'll just ask the organizers about that. 1 second. Yeah, but till then, if someone can tell me the space and time complexity. Uh, so, yeah, anyone space and time complexity? I've asked the uh, organizers for the attendance. Uh, so, O of 1 space because space O of V time. Okay, so some people are saying everyone pretty much agrees that the time complexity is O of n. Some people are saying the space complexity is O of 1, some are saying it's O of n. Uh, first of all, obviously, we will have to store the graph somehow. That will take some space up. That will take like O of n space or something. We will have to do that. But if we exclude that, that will obviously exist in each and every problem, right? So now the next thing is how much space does the traversal algorithm require? You need to maintain a visited array, right? Obviously, visited array is of length n, right? So the space complexity is also of n, and yeah. So the people who are saying the space complexity is O of 1 are wrong. It's like O of n because you have to maintain a visited array. It's standard DFS. If you don't know what DFS is, it's fine. I'm just like this is anyways an algorithm which is rarely used. But yeah. So yeah, with hair tortoise, the space complexity is O of 1, and that is basically the only algorithm, the only advantage. There are some problems where you have to use Floyd's algorithm. Like there are obviously variations; they're not direct applications. Uh, like I remember seeing a problem like while I was reading about this. Uh, while I was making the presentation, 2400 rated code was a problem which was similar, very similar to Floyd's, but yeah, otherwise it is not a very widely used algorithm. And I think I still have the problem open. Okay, no, I don't have it open. So yeah, we'll just describe the algorithm. So the algorithm, we maintain two pointers, a slow pointer and a fast pointer, and both of them start at the head of the graph or the singly linked list. Like in this case, they would start at 1. So on in each step, we move the slow pointer ahead by one edge and the fast pointer ahead by two edges. That's the reason they're called slow and fast, right? So like both of them point at 1. In the next step, the slow pointer will point to 2, the fast pointer will point to 3. Then in the next step, the slow pointer will point to 3, the fast pointer will point to 5, and so on. And yeah, that is basically what we do. So the question comes is how do you find direct whether there's a cycle? So yeah, sorry. So let's say at any point they both end up on the same node. So then a cycle must exist, or else if basically both the pointers reach an end is basically not both. Sorry, if any one of the pointers reach an end, then at that point we stop the algorithm and we say there is no cycle in the graph or the singly linked list for that matter. And what is an end? It is basically a node which has no outgoing edge. And we will so let's just look at a visualization of why this works. Like I'm not going to prove it, but this part, this one is fairly obvious. What is not obvious is why does finding the starting point works. So initially both of them were at 0, then the slow pointer which is in green has moved on to 1, and the fast pointer has moved on to 2. Then the fast pointer moves on to 4, the slow pointer has moved forward by 1 again, and now you will notice both of them are in the cycle. So essentially, the fast pointers now they both are going to just keep looping over the cycle, and the fast pointer will keep catching up uh, to the slow pointer, and eventually they will end up on the same node. So yeah, you can basically see it's. I'm not going to cover the proof again. The proof is it's not hard as such, but it's just uh, not needed because it is. This is a fairly intuitive thing that they both will end up on the same node. They're both in the same cycle. One is moving forward by two, other is moving forward by one. At some point, they will collide. And if there is no cycle, then obviously we will end up at some endpoint and we will stop there. So this works. The next part is finding the starting point. So we want to find the starting point. If you remember, starting point is the point where we enter into the cycle, which is point 4 in this graph. So this is something which is not obvious, and but let's just cover it first. So we have two pointers, the slow and the fast one. Let's say the slow is A, fast is B, and so we move them till they meet each other. That is like when we have figured out that they have a cycle. And now, if we now know that they have a cycle, we reset the slow point. Like both of them are at the same point, so we could reset each one of them. But let's just say we reset the slow pointer to the head, so the initial starting point, and then now we move both the pointers one step at a time. So instead of the fast pointer moving two steps at a time, we just move them one step at a time, and then the algorithm basically says that the first the point at which they meet again is the starting point, and that is this is just the pseudocode is SUCC is the successor, so it basically points to the next node of X, the node which has an incoming edge from X, or no, yeah. So A is successor of X, B is successor of X. While they are not equal to each other, we just keep doing it again and again. We reset A to the starting point. While they're not equal to each other, we keep moving them one step forward, and then first becomes equal to the point which they have met at. And yeah, let's just see the. So now the one of the pointers got reset. They both move forward by one. They both move forward by one, and they meet at the starting point. So we can do this for another graph. And yeah, you can see the meter, the starting point. Uh, why this works is not particularly obvious. And again, it is here, they meet at the starting point. Why this works is, I'm not going to go over the exact proof, but basically, the number of steps it takes for them to reach the point where they first collide at is going to be a divisor of the length of the cycle, and that is the reason it works. Basically, just modular arithmetic. It is nothing too fancy. You can easily find a proof online if you search for it. But yeah, this is not intuitive at all. I'm just stating the algorithm to show like different kinds of things two pointers can be used for. And the length is obvious. Like you have found the starting point, you just keep go around the cycle till you hit the starting point again. And yeah, that is it. And yeah, this is just the same thing that I just explained. And yeah, some of the resources which I've used for making this presentation. And yeah, I think that's the end of today's session. I can take any doubts if someone has. Some people had doubts, I think. If someone has doubts, please like repost it, or else I'll like I think the session will end. Like I think someone had a doubt in something. I think someone else is presenting. लास्ट वाला समझ नहीं आया. लूप वाला. कौन सा लूप वाला? Will you post? Yeah, I'll send it on Discord. Like the organizers will send it. Yeah, wanted to use it. Wait. Uh, Wait. One by one. Last what loop wala? Wanted to use set. Oh yeah, can you just post your code again? I'll just look at it now. Yeah, slide will be posted on Discord. Last problem. Wait. The cycle thing or the last problem as in the cycle thing? Cycle. What loop wala? The length. Which part? Length, starting points, whether a cycle exists. Just write which one. Cycle. Uh, okay, so see the idea behind the cycle essentially is that uh, they both the pointers will enter into the cycle, and one pointer keeps moving ahead by two, the other pointer keeps moving ahead by one. How they are moving? Uh, Wait, I'll just generate a big graph. Yeah. Okay. So how are they moving? So the orange pointer, the fast pointer, it moves forward by 2 steps. So notice that the orange pointer is at 4 and the green pointer is at 2. In the next step, the green pointer will go to 3, the orange pointer will go to 6, and so on and so forth. That's it. And what else? Yeah, look at the set code. While less than array dot size, set dot insert array are. Okay, slap box. The reason this would work is like let's just say uh, you have an array, let's say 1, 2, 3, 3, 4, 3, 3. Uh, Set code is just logic. So see, the thing I'll tell you the reason why the set code won't work. You need to basically count an element if it exists only one time, right? So let's say an element occurs 3 times, right? So you remove it, or like let's say an element so is 1, 2, 3, 3. So you insert 3, right? You do set dot insert array r, and let's say the size does not go above k. But now the next element is again a 3, as you can see on the screen. So you need to ideally remove the element from the set, but you are not doing that. So that won't work. You need to maintain a map with like uh, where the value is the frequency, or else you set could work, but you have to use a multi set in conjunction with it. Any other doubts? Or I think we can end the session. I think no other doubts. Uh, yeah, I think thank you.
Hello everyone. Am I audible?
Yeah, yeah.
Okay. So thank you, Ashish, for the great session. And I'm here to announce one thing. Like we are sharing problem set as a PDF till now, but from now on we will list the problems on the this mark.in courses website, and the link is already in the description box. Here you can go to the topic, like I can show it like in the dynamic programming. If I go to classic DP problems, uh, I can find like there are these many problems are listed for a practice, and you can mark the problem like you are solving, you solved, or you skip the problem for your like better practice, and you will get a better interface to practice the problem. And you can also find some other courses listed on monk.it, so you can learn them along the way you are learning the problem and practicing the problem. So thank you for it. Or if you have any other doubt, you can ask in the comment. Okay, so from now on, you will find every practice problem on the monk.in platform, and we already set the link in the description box, and we will share a link in the Discord announcements as well. So thank you for joining the session, and I think we can end the session now if you guys don't have any other doubts. Okay, if you have any doubts in these problems, you can ask the doubt in the Discord doubts channel and ping the IICPC team, and their other students can also help you if they already solve the problem. So, do you guys have any other doubt, or if not, we can end the stream. Okay, I think it's good to end the stream now. Thank you. Thank you for joining in.